We're going to do some problems, friction on the horizontal plane first. We put a block on a plane, it's at rest, it weighs 15 newtons. I pull with 4 newtons, it's still at rest. What's the force of friction? It's got to be 4 newtons because it's not going anywhere. The sum of the forces has to be 0. And it's static friction. Now I increase that force of the pull to 6 newtons. At that point, the block starts to move forward. What's the force of friction static maximum? Static friction rises to meet this pulling force until it can't go anymore. You reach the maximum at 6 newtons, and then it jumps forward. And this is exactly what you saw in the lab. Go calculate the mu static. You got to know your formulas. And we get 0.4. Now, don't forget where that formula came from. It came from this graph. We did many trials, and we found the slope of that graph. That's why it's force of friction static over the normal force. This is only one data point, and in a lab, you would want to do many data points by putting more weight on there, and then finding the slope of the best fit line. So the block is now in motion, and the force of friction static has been broken. It's now reduced, and this force, if it maintains that present value, will cause the block to accelerate. Well, we're going to reduce that pulling force to 4.5 newtons, and at that point, the block moves at a constant velocity. Now we know that this friction has to equal that because we're going at a constant velocity. What is that force of friction? Obviously 4.5. Is it static or kinetic? If it's moving, it's kinetic. Now you can find the coefficient of kinetic friction. You use your friction formula, you got 0.3, and there's your kinetic coefficient of friction. Remember that now. Now I'm going to reduce the pull to 2 newtons. That pull is less than the force of friction. The force of friction is still 4.5 newtons because the block is moving. It doesn't matter if the block is speeding up or slowing down or moving at a constant velocity. As long as it's moving, that's your current force of friction. Well, what happens? If I'm only pulling with 2 and that's going back with 4.5, the block's going to slow down. Now let's try friction on an incline. Let's take the same block, put it on the incline, let it go from rest. If the angle is 12 degrees, what's going to happen? Well, we have to think about this a little bit. It's the same block on the same surface, so the coefficients of friction, they're still the same numbers. So let's get our parallel and perpendicular components of the weight. Well, we have 3.12 newtons from gravity pulling it down the plane. Let's find out what the maximum static friction is and see if this will pull it down. Rearranging the friction formula, I get a maximum static friction of 5.87 newtons. Well, that's how much friction could be developed going up the plane. But we're only pulling with 3.12 newtons. Well, that's not enough to break static friction. So what's going to happen? The block will remain at rest. So now we can ask, what is the current force of friction? Well, if the block's remaining at rest and there's 3.12 going down the plane, there must be 3.12 newtons going up the plane. So we really don't have 5.87. We only have 3.12. And of course, it's static. Well, the next part is, how hard would you have to pull to get the block to start moving down the plane? Well, which way would you pull? Well, I want it to move down the plane. It's not going down the plane, so I'm going to pull down the plane. That means the component of gravity pulling down the plane and you pulling down the plane have to add up to break static friction. Can you picture the math? If you have to, you could write an equation. The force going down the plane due to gravity, plus you're pulling down the plane, has to overcome this force of friction static maximum. Solve for F pull. And you get 2.75 newtons. As soon as I pull a millionth of a newton more than that, this is going to break and it's going to come down. Well, let's try problem 3. It's the same block and plane at the same angle. And we're going to tap the block to start it moving down the plane. What happens? Is it going to speed up? Is it going to slow down? We'll draw the free body diagram and take a look at the force going down the plane and compare it to the force of friction kinetic. It says that it's moving. So I can use mu k. It's the same plane and block, so it doesn't change. Same number as before because it's the same angle for the normal force. I get a force of friction of 4.40 newtons. That means I have a friction force up the plane that's kinetic of 4.4 newtons. The gravity is pulling down at 3.12. It is moving, but because that force is bigger than that force, it's going to slow down. At what angle will it go down at a constant velocity? We're going to now have to change this angle. That's not big enough to maintain constant velocity. We're going to have to increase the angle. We know this formula, and we know that each of these terms are equal to these terms when we're going down at a constant velocity. This is the formula for the force of gravity pulling it down the plane. Well, that's got to be equal to the force of kinetic friction if we're moving at a constant velocity. The normal force is just Fw times cosine theta. What's going to happen to the Fw's? Isn't that nice? They cancel out and we're left with tangent theta. But that's a very special theta. It's the angle at which it will go down at a constant velocity. Because we set this equal to this, then that's got to be that angle. We know the coefficient of kinetic friction is 0.3. It's the same block in the same plane. Do the math and you get 16.7 degrees. Yep, it's bigger than the 12. Need more practice? Go back and watch the videos I'm making. Take a look at those worksheets that I give you with the answer keys. I have chapter notes with tons of problems worked out in there, step by step. And you can always let me know when you need to talk. We'll get on a Zoom call. So now, finally, what formulas do you need to know? Sure, you need to know trig, just like we've been doing so far all year. We have now added 2 formulas to our physics repertoire. This is the only new formulas we've got.